In this lecture, we discuss mixing problems for one single compartment. So let's first remember or define concentration as the ratio of weight divided by volume. And we're going to be discussing mixing problems where there are substances that are a perfect mixture in a sense, and so that term of perfection in mixing is also known as homogeneous mixing. So perfect mixture is also known as homogeneous mixing. An example of this could be sugar on water or salt, a solution of salt on water. The idea of a compartment is visualized usually with square or rectangle. So we will have a quantity considered a state variable, and we can consider a rate at which this state variable has a gain. For example, let's say that this rate here is proportional to the state variable, something that we write as beta y, and let's say that there is a loss of the amount of whatever the quantity, whatever the state variable is measuring. Let's say there is a loss denoted here at a rate also proportional to the state variable, something that we would write as mu y. So this rate in and also the rate out, rate at which there is a loss of this, they will come into play in writing something like the rate of change of that state variable is going to be equal in this case to beta y minus mu y. So really what we mean by writing equations of this type is that the total rate of change is the result of considering the subtraction of the rate in minus, in other words, the gains minus the losses, minus the rate out. Now let's consider the following scenario of a tank that has initially 40 pounds of salt dissolved in 600 gallons of water. At this point, let's pause the video and read this word problem. So in this case, we're going to denote the state variable as q of t, and the first task would be to write down a differential equation for q of t, assuming that time is positive, with the ultimate goal of solving the differential equation and therefore establishing what is the limit of q of t as t goes to infinity. So first, the state variable here is in terms of q of t, which denotes the quantity of salt in the tank. And we're interested on the rate of change. We're going to formulate a differential equation in terms of the rate of change of the quantity of salt in the tank. So we're going to formulate that the rate of change of Q is going to be equal to the rate in minus the rate out of the tank. So we illustrate this with a compartment where Q is what's that amount of salt in the tank, and so we have an arrow pointing towards the tank with information here of 4 gallons per minute, and also rate information about the rate out, also happening at 4 gallons per minute. They happen at the same rate. So the rate in is going to be equal to 4 gallons per minute multiplied by 1/2 pound per gallon. So here's where we have to scale that information of 4 gallons per minute, because we know that starting at time t equals 0, water that contains 1/2 pound of salt per gallon is poured into the tank at a rate of 4 gallons per minute. Okay, so putting together those two pieces of information, you can see how here basically we're going to end up with units here, pounds of salt per minute. And we also are going to simplify this expression, and we're going to end up with 2 pounds of salt per minute. That is what we're going to have as a rate in. On the other hand, concerning the rate out, for every minute that passes, there are 4 gallons of mixture. This is homogeneous, well mixed or well steered solution. 4 gallons of mixture that are removed out of the total of 600 gallons. So let's write that as a ratio. Okay, so we have 4 gallons per minute divided by 600 gallons. So this would leave us with the number 4 over 600. We can do this in a couple of steps. 1 over minutes, and here we're going to have gallons over gallons, which are eventually going to cancel each other. So this reduces to the number 1 over 150. This is by simplifying this fraction, 1 over 150 per minute, with units minutes to the -1 or 1 over minutes. So if there are Q of t pounds of salt at time t, when we multiply that quantity Q of t times this rate, 1 over 150 per minute, this is going to give us, this is in other words, Q of t over 150 with units here, pounds per minute. So Q of t is something that's measured in pounds of salt, and this would be a way of expressing the rate out. So the rate of change of Q is rate in minus rate out, which means that this looks like 2 minus Q over 150. The units are, I'm going to write them here just below, pounds per minute. That was the units, those were the units we obtained for rate in, and the rate out also has units, pounds per minute. So this checking that the units are consistent is important, because since we're subtracting these two things, then the units of the rate of change are still in pounds per minute as expected. So in summary, what we really would like to do next is to solve this initial value problem, where the initial condition is Q evaluated at 0 equals 40. And to do that, we rewrite this differential equation rewriting this differential equation in this form, we can easily notice that this is indeed a linear ordinary differential equation. It's linear in q and the first derivative of q. So we're going to proceed to compute the integrating factor. Here the coefficient is a constant function of t, so we will compute the integral of 1 over 150 with respect to t. That integral equals t over 150, and then the integrating factor will be the exponential of t over 150. So we go back to the linear differential equation and multiply each term on that linear ODE by the integrating factor, which implies that we can write the derivative of a product, and so the next step is that we would integrate derivative of a product, the product rule, if you will, on the left hand side, and now we integrate with respect to t in both sides of this equation. That leads to the following expression: e to the t1 over 150 times q equals 150, which comes out of using substitution or change of variables, 150 multiplying the existing coefficient of 2 times that exponential, and here we're going to write a constant m here as the constant of integration. So what we do next is to solve for q, which implies that by multiplying this exponential by every term in this sum, so we end up here with 300 plus, I'm going to write the constant first, m times e to the minus t over 150. And this would be the expression we obtain for q of t. So next, we're going to determine what is that value of that constant of integration m by employing the initial condition. At 0, q takes the value of 40, but we can also evaluate this right hand side here. So we would have 300 plus m times e0. So we can easily solve for m to find that minus 260 is equal to that constant m. And so that means that q of t looks like 300 minus 260 times e to the minus t over 150. So it's straightforward to compute the limit of this expression as t goes to infinity. We do that, then we would obtain 300 minus 0, which means that that limit equals to 300. So let's now use the one-dimensional flow analysis to validate that result. To consider this linear differential equation, we observe that this right-hand side is entirely a function of the state variables. It's an autonomous system. This expression is a line with negative slope and positive intercept with the vertical axis. So we consider this plane where q, the state variable, is on the horizontal axis, the derivative of q is in the vertical axis. The intercept of this line here is what we're calling f of q. That intercept with the vertical axis is 2, and this equilibrium point here would be equal to 300. So, and remember that equilibrium point comes from solving this equal to 0, right? So if you solve here for q, you can easily see where that 300 comes from. That's the point of intersection of this line with the horizontal axis. Now, on this region here, Q prime is negative, and that means that Q would be decreasing. The arrows and the flow are going to be pointing towards the left. In this other region, Q prime is positive, which implies that Q is increasing, and here the arrows and this one-dimensional flow will be pointing towards the right, which means that this equilibrium point is stable. So now I would like to translate that information in the horizontal axis into this plane where Q of t appears in the vertical axis and the independent variable t appears on the horizontal axis. There is an equilibrium point which is positive. In this case is 300. Okay, so this would be 0 on the vertical axis, and these arrows are pointing as follows. They're for things that are between 0 and 300, they are pointing towards 300, and things, if we go above 300, then they're pointing towards it, right? So this is the idea of this point being stable, that the arrows are pointing, are convergent to it. And so that means the solutions, the time solutions, are going to converge to that horizontal asymptotic level. So this would be one time solution for one specific initial condition for Q of t, and if we initialize somewhere closer to 300, then this would be how that other solution looks like, and if we initialize a little above it, then the solution is also going to converge to that level, and so on.